Hello everyone from Math 2200, Discrete Mathematics. It's Professor Winston here again with a video going over your Books section 11.3 titled The Pigeonhole Principle. All right. The pigeonhole principle is a mathematical tool used to establish that repetitions are guaranteed to occur in certain sets and sequences. The pigeonhole principle says that if n plus 1 pigeons are placed in n boxes, then there must be at least one box with more than one pigeon. So the image they're showing us here, right, if you had 10 pigeons and had to place them in 9 boxes, you could put one pigeon in each of the 9, but then the 10th pigeon would have to share a box with someone. That's what this is saying, that at least one of the boxes will have more than one pigeon. If the number of pigeons is more than the number of boxes. I'm hoping this is pretty intuitive, makes a lot of sense. Because this can be applied to a lot of things though. So yeah, although the principle itself appears to be obvious, it can be applied in clever ways to prove facts that are quite surprising. Below is a more mathematical version of the pigeonhole principle stated in the language of functions. Alright, so here's the same statement kind of reworded. So if a function f has a domain of size at least n plus 1 and a target of size at most n, where n is a positive integer, then there are two elements in the domain that map to the same element in the target. Right? In other words, the function will not be one-to-one. And I'll let you read the proof here. I don't want to get into the proof really right now. So in the mathematical statement of the pigeonhole principle, the elements of the target represent boxes, and the elements of the domain represent pigeons. All right, the function f maps the pigeons to the boxes. Alright, so their first example after this is, well, consider a person who has a drawer filled with socks. Each sock is either blue, gray, or red. How many socks does the person have to get from their drawer before he knows that he has a pair of the same color? So in this case, the domain is the set of socks picked from the drawer, and the target is the set of sock colors. The function f maps a sock to its color. The pigeonhole principle says that if the socks come in 3 colors and 4 socks are selected, the person is guaranteed to have a pair of the same color. Alright, so this is if you were, picking the socks out of the drawer blindly, not actually looking at the socks. So it's like, hey, so what could happen is, the first one's blue, then the second one could be gray, and the third one's red, right? I don't have any pairs yet of the same color, but then when I pick that 4th sock, it's going to be either blue, gray, or red. So I'll have to have a pair of some color. Hopefully that makes sense. Here is another application of the pigeonhole principle. Among any set of 13 people, there are at least 2 people who have a birthday in the same month. Right, because there's only 12 months. So the function here would map, the people, the 13 people would be in the domain, and then the target would be the 12 months of the year. And since there are more elements in the domain than there are in the target, at least it's not going to be one-to-one. It can't be one-to-one. So there's got to be 2 people, at least 2 people that map to the same month, that have a birthday in the same month. Now, if there are 12 or fewer people, then the pigeonhole principle can't be applied, right? Because if you had 12 people in the domain, 12 in the target, it could be 1-to-1. This is an interesting problem here. I'll play the animation for you. Now consider a fast food chain that is selecting store locations in a 2-mile by 2-mile square. So 2 miles on all 4 sides. The pigeonhole principle can be used to show that if 5 stores are placed in this square, then there will be 2 stores, at least 2 stores, within the square root of 2 miles of each other. So let me show you this. Right? So they start off with this 2-mile by 2-mile square. And they divide it into a grid of 4. They're placing 5 stores. So you could think of the 5 stores as being in the domain. So they're, so just to ensure that the function's not 1-to-1, and I can apply the pigeonhole principle, we divide this area up into 4 or fewer regions. Because again, the domain has 5 elements, these 5 stores. So in order to ensure that the function I'm creating is not 1-to-1, I'm going to divide the region up into 4 equal regions, which they've done here. And if they do it this way, each of these squares is now a mile by a mile, right? A nice square mile in each of these. Now the largest distance, they go even further, right? Say they tried to keep them as apart as possible. Well, if you place these at the corners, one in each of these squares, the 5th store has to go in one of these squares again, right, by the pigeonhole principle. And the longest distance between points in any of these squares is going to be the square root of 2 miles. Okay, so that means that, that tells me that there's got to be at least 2 stores that are within the square root of 2, about 1.4 miles of each other. So hopefully so again, another interesting application of that principle. Alright, so our activity here. We're asked to indicate whether the pigeonhole principle can be used to prove the following statements. So a class of 11 students take a quiz that is worth 10 points. No partial credit is given, right? So you either get 10 points or 9 points or 8 points. There's no half a point or anything like that. So if every student received a score that is an integer, there must be at least 2 students who receive the same score on the quiz. Well, let's think. And I'll pull up a piece of paper here. My domain is these 11 students. I'm going to try to create a function here. So the domain is the students. So student 1, student 2, right down to student 11. And the target are the possible scores on this quiz. Now, the quiz is worth 10 points, and it said no partial credit is given. And it also said, every student received a score that is an integer. Well, can't you score 0 as well? So a student could have scored a 0, a 1, all the way up to 10. So there are 11 elements in the domain, and there are 11 elements in the range, or the target, right? So this could be a 1-to-1 function. I can assign each of these 11 to a different score. So the function could be 1-to-1. Doesn't have to be, but if it could be 1-to-1, then we're not guaranteed that 2 will go to the same score. right, that 2 of these students had the same score. So this is a false statement. So I'm going to say no. How about this one? Among a group of 400 people, there are at least 2 who have the same birthday. Absolutely. All right, now my domain, say, is the people, and the target is days of the year, and I just associate a person to their birthday, draw a little arrow. Well, there are 365, unless it's a leap year, 366 days in a year. So there are more elements in the domain than there are in the target. So it has to be, not 1-to-1. It can't be 1-to-1. So there has to be at least 2 different people with the same birthday in this group of 400. Would it apply here? Nope, right? This is only a group of 350 people. 350 people in the domain, 365 days in the target, that could be a 1-to-1 function. So it's not guaranteed that at least 2 of them have the same birthday. How about here? There are 4 people whose weight is at least 100 pounds and less than 130 pounds. So 4 people that weigh from 100 to 130 pounds. There must be at least 2 people in the group whose weight differs by at most 10 pounds. Okay, so this is, I'm telling you right now, this is similar to this problem here. Let me show you. I'll draw this up. So let me draw a little number line. And imagine these are, weights of people in pounds, in lubs. Right? And they said that these people, these 4 people weigh from anywhere from 100 pounds to 130 pounds. All right, and we have 4 people, which I'll mark off with orange dots. We have 4 people. Now, in order to be able to apply the pigeonhole principle, I'm going to assign a person to a weight. There are 4 people. In order to be able to apply this pigeonhole principle, I would like to then divide this up into 3 regions, right? 1 less than the number of people. So that way the elements in my domain, there are more of them than there are in my target. So I'm going to divide this up into 3 regions. Now if I do this, that'll be from 100 to 110, and then from 110 to 120. That'd be nice. That doesn't matter what 3 regions, but make it 3 equally spaced regions to make it nicer. So I break this up into 3 regions. Let's say region 1, region 2, region 3. Interval 1, interval 2, interval 3. So this first person, say, weighs 100 pounds exactly. And then, they're in this region, they're in this region. So I've gotten rid of 3 people. Now the fourth person has to be in one of these 2 with somebody else, has to share a region. And if you share a region, the difference in your weight is at most 10 pounds. I mean, you could have 100 to 110, but the difference is at most 10 pounds in any of these regions. And by the pigeonhole principle, 2 people have to share one of these 3 regions. So yes, 2 people have a weight that differs by at most 10 pounds. And then you know what? I'll leave this one to you, because this one is almost exactly like the animation problem. Pretty much exactly like it. But instead of 2 mile by 2 mile, you get a 6 mile by 6 mile square area. Alright. So now they're generalizing this, right? So instead of placing n plus 1 objects into n boxes, you're just placing, you know, a number of objects into some fewer number of boxes. Right? So the pigeonhole principle can be used to show that there are at least two of a given type of item. For example, in the socks example, right? What if it is important to have more than two of a given type of item? So consider the ridiculous situation, they're saying. Consider the situation in which a pair of twins are picking socks from a drawer. And again, this is a drawer with blue socks, gray socks, and red socks. And suppose they're picking them out blindly. Right? They're not actually looking specifically for a pair, but they want to have two pairs of matching socks, right? So they can match each other. Right? So not only do the socks in each pair have to match, but the twins also want to wear socks of the same color. How many socks must be drawn from the drawer to guarantee that they have 4 of the same color? So after they pick, so they must pick the 10th sock, right? Because again, this could happen. This is one possibility. Maybe they picked out 3 blues, and then the next 3 were gray, and the next 3 were red, and oh man, so far I don't have 2 pairs of the same color. But then that 10th sock is going to be either blue, gray, or red, and then I'll have 4 of some color, and therefore 2 pairs of some color for the twins to wear. So the 10th sock will make a set of at least 4 socks, which are all the same color. All right, so this general rule is stated here mathematically. So consider a function whose domain has at least n elements and whose target has k elements for n and k positive integers. Then there is an element y in the target such that f maps at least the ceiling, right, remember the ceiling function, of n divided by k elements in the domain to y. Right? And again, they run through a proof here. I'm not gonna run through the proof. So back up in this example. The target was the colors, right? Blue, gray, and red. So if the target was 3, 3 big, the target had 3 elements, had a cardinality of 3. And you see if the domain has a cardinality of 10, I pull 10 socks and assign each sock to its color. 10 divided by 3 is, 3 1/3. And the ceiling of 3 1/3 is 4. So if my domain has 10 elements and the target has only 3 elements for a function, there are at least 4 elements in the domain that will map to the same element in the target. It's got to happen. All right, so that's the generalized pigeonhole principle. And they explain that here. All right, so let's think. Can this pigeonhole principle be used to demonstrate that each fact is true? So among a group of 50 people, there are at least 5 people whose birthday fall in the same month. All right, so again, I'll draw a little picture again where I'm setting up a function. So again, my function here, the domain is people. Person 1, person 2, person 3, all the way down to person 50. And I'll assign each person to the month that they were born. All right, so January, February, all the way down to December. All right. So again, you see definitely more people in the domain than there are in the target. So this is definitely not going to be 1-to-1. But they're saying, could I guarantee that 5 of these people will go to the same object? Well, let's see. If I put the first four, let's say I grouped them by fours. Say just I grouped them by U4. This could be a possibility. 4 people go to January, and then 4 to 8 go to February, and then basically I'd go to 48. Persons 45, 46, 47, and 48 would then go to December. That's 4 arrows. That's 4 arrows. So you see there, every month has 4 arrows going to it, but there are still 3 people left. Or I'm sorry, 2 people left. Person 49 and 50, and they got to have a birthday somewhere in some month. So let's say person 50 there. Now there's the 5th arrow. There's 5 arrows going into December, and any one of these months would have to have at least 5 arrows. There's one month that has at least 5 arrows going to it. Now again, if you take the size of the domain divided by the size of the target and look at the ceiling of this, right now 50 divided by 12 is 4 point something. It's 4 and something. 4 and 2/12, 4 and 1/6, 4.16666, whatever. But the ceiling would be 5, right? So this is what that generalized pigeonhole principle tells us then, is that there's at least one element in the target that has 5 elements in the domain mapping to it, right? There are at least 5 people that have the same birth month. So yes, we can state this from the generalized pigeonhole principle. How about this one? Alice bought 14 cups of coffee in a week. Can you say this? Then there was a day in the week in which she bought at least 3 cups of coffee? No. She could buy 2 every day. All right, there's 7 days in the week. So again, each cup of coffee is in the domain. So 14 elements in the domain. Every day of the week in the target, 7 elements in the target. 14 divided by 7 is 2. And the ceiling of 2 is 2. All right, remember the ceiling of an integer is itself. So the only thing we can guarantee from this pigeonhole principle is that there's going to be a day where she had at least 2 cups of coffee. All right, but you can't guarantee that she had at least 3 cups on one day, because she could just have 2 every day, right? So I can't apply that here. Can't say that. Here, a group of 42 employees are assigned to 7 different printers. So 42 divided by 7 is 6. So I can guarantee that at least one printer is going to get 6 employees assigned to it, but I can't guarantee that one of the printers is going to get assigned 7 employees, right? Because again, I could assign 6 employees to each printer. And there you go. I can't guarantee that there must be a printer with at least 7 employees assigned. Right? Okay. All right, so in many situations, one would like to know how many items are required to guarantee that a certain number of a given type, right? Just like the one with the socks, where they asked how many socks would they have to pull to get those 2 pairs of the same color. So you have to answer questions like this. So here, in the approaching problems, so this is like the converse. You're just going backwards. You're going backwards. You want to know how many elements need to be in my domain in order to guarantee that so many elements map to the same thing in the target. So their first example here is in the approaching problems, like the student committee problem. It is useful to think about how one could avoid having 4 students from the same class sign up for a committee. All right, so you got this school and this class, and they're trying to form a committee with well, I guess the problem starts up here. All right, so let's do it up here then. So the school. All right, so consider a situation in which a school would like to select a group of students to form a committee. that will meet regularly in order to plan an event. Because students from different grades have different schedules, the group must all be in the same grade. The school has students in grades 9 through 12, right, so 4 different grades. And the goal is to have at least 4 students on the committee. Right. The school puts out a sign-up sheet for students to indicate their interest in participating in the committee. How many students need to sign up in order to guarantee that there will be at least 4 in the same grade? All right. So again, they're telling you, think of the worst case scenario where 3 sign up from each grade. All right, 3 sign up from each grade. So far we haven't, that's the worst case scenario. We haven't gotten our committee yet. So that's, 12 people. The 13th person has to make up that committee then. Right? Because if, 3 people are from, each grade, the 13th person would then guarantee you have at least 4 people from the same grade. And then you can have your committee. All right, so the answer here would be 13. So again, really what you're looking for is, the solution to this kind of equation. All right, the target had 4 elements. So you're trying to figure out what's the size of the domain. All right, what's the minimal size? Find the minimal size of the domain to guarantee, this is size of the domain n, to guarantee that this was 4. Right? To guarantee that this was 4. So again, the worst case scenario, when n is 12, 12 divided by 4 is 3. Right? 12 divided by 4 is 3, and the ceiling would be 3, not 4. So n could be equal to 13, 14, 15, or 16, right? But then once n is 17, the ceiling is 5. So that minimal value is 13, right? You solve an equation like this, right? Trying to figure out what, what's the smallest size the domain needs to be to guarantee that at least one element in the target has 4 elements mapping to it, right? Has 4 students from the same grade. And they describe that here. You can play around with this. Read. I'll let you read all this. This is a lot. So let's look at some problems. All right, so give your answer as a number instead of a word. Okay. So here, a group of students is selected from a class. Every student in the class is either in 3rd grade or 4th grade. And no student is in both the 3rd and 4th grades. Okay. How many students must be selected in order to guarantee that at least 5 3rd graders or at least 5 4th graders are selected? So basically they want 5 people from the same grade to be selected. So again, we're kind of solving this equation. I need to know how many people can I select? And remember, they're from 2 groups. They're from 2 groups, 3rd grade and 4th grade. And they want to guarantee that at least 5 are from the same group. So again, you could do this like draw a little picture, make a little diagram. Here are the 4th graders, the 3rd graders. And again, to start marking off, hey, you select a 4th grader, a 3rd grader, another 4th grader, another 3rd grader, another 4th grader, another 3rd grader, another 4th grader, another 3rd grader. Now you have 4 of each. Then the next person you select, right, has to be in either camp. The next person guarantees that I'll have at least 5 from the same grade. So n equals 9 here, right? And again, just think of what would give me 4. What would be the largest it could be to be 4? What divided by 2 is 4? 8 divided by 2 is 4. and then anything bigger than 8, when I divide it by 2, will be 4 point, bigger than 4, and then the ceiling, when n is 9, it's 4.5, the ceiling is 5, right? I go one bigger than that. 8 divided by 2 is 4, one bigger than that will guarantee that I have a ceiling of 5. Right? So yeah, I would have to select 9 students to guarantee that at least 5 of them are from the same grade. Here, a research firm is tracking the number of text messages sent by 1,000 7th graders in a single day. How many texts must be sent by the group in order to guarantee that at least one of the 7th graders has sent at least 20 text messages? All right. So here, you got these 1,000 7th graders, right? How many of these texts must be, basically, I want to look through each of these and make sure that the ceiling is 20, right? Somebody sent at least 20. So think about this. Now, here this is a little different. They kind of give you the size of the domain, don't they? Because you can have, the text over here, and then students are the target, and then have every text that's sent by a certain student mapped to them. And I want to know how many texts do there need to be, or how many texts do I need to go through to make sure that at least 19 of them are going, or at least 20 of them, I'm sorry, are going to the same student. Oh, I did say 1,000 7th graders. All right, sorry. So there are 1,000 7th graders. They're asking how many texts would they need to search through to make sure that they know they have a group of at least 20 texts that were sent in the same day. Sorry, they did say there were 1,000 7th graders. So I know the size of the target. I want to find the size of the domain. So it's the same kind of problem. So again, just think, each one of them could have sent 19, right? Maybe the first bunch I looked through, if each one of them sent 19, that'd be 19,000. So I would need to check 19,001 of them. I'd need to check 19,001 texts to guarantee that I have at least 20 of them from the same student. Right, again, you're always thinking about the worst case scenario. Right, what if the first 19,000 I checked, I only saw 19 from each one of them? Right, then the next one has to make it so that I'm looking at 20 texts from the same student. Right, so this is 19,001. Right. Okay. All right, now some more uses. These are some nice ones. All right, now I'll just read some of these off, and not all of them. All right, but more uses of the pigeonhole principle. Okay, so here it says, below is a list of 25 6-digit numbers. The pigeonhole principle can be used to show that there are two distinct subsets of the numbers listed below that add up to the same value. So I could use, again, you could use this pigeonhole principle to take these, 25 6-digit numbers, and you can show that it's guaranteed that there are two different subsets of numbers. So maybe these 4 and these 5 that add up to the same value. So here, the function maps each subset to the sum of its elements. So for example, the subset consisting of the first two numbers in the first column, these two here, would map to 961,195, right? Because that's their sum. The target, right, is the set of all possible values for the sum, right? All possible sums of a subset of numbers. The value of each number is at most 999,999. Since there are 25 numbers, right, the sum of any subset of the numbers is at most 25 times that, right? Because if you were to grab all, take the subset of all 25 of them and add them up, they can't be any bigger than this. What is this? 24,999,975. Therefore, the possible values for the sum of a subset falls in the range from 0 to this 24 million something. Now this is 24,999,976 options, right? And that's at most. And really it's smaller than this because yeah, 0 is a possible sum because you could take a subset with no elements and get a sum of 0. But then you just look for the smallest number in here. Whatever the smallest number is, the subset with just that number is the next highest sum possible, and then all the sums after that might be possible. So you could cut this down actually, but they keep it. So there are 24,999,976 possible sums that each of these subsets could map to. Now, if you recall from our chapter on counting, if you have 25 objects, how many possible subsets are there? Well, there were 2 to the 25th. And 2 to the 25th is huge. And that number, the number of subsets, the number in the domain, is greater than the number of possible sums. So there's at least 2 subsets, 2 distinct subsets that'll have the same sum. Right? Note that while the pigeonhole principle establishes that there exist 2 subsets that sum to the same value, it doesn't say anything about how to actually find them. All right. I mean, if you actually wanted to say, okay, at least two subsets of these numbers have the same sum, great. Can you find them? Well, that would take a lot more work. You'd actually have to play around with these. Right, so this just shows you that certain things exist, right, not how to find them. I'll let you read this one. If you don't know what continued fractions are, I wouldn't worry about it. You can even skip this. You've seen enough examples by now of the pigeonhole principle, and I'll let you play this animation as well. This video's over half an hour long now. Alright, so let's just get to this last activity and the challenge activity here. So here, the largest 2-digit number is 99, right? How many 2-digit numbers must be in a set in order to apply the pigeonhole principle to conclude that there are 2 distinct subsets of the numbers whose elements sum to the same value? Right. So this is kind of like our problem here, right, the example here. So let's think about this. All right, I'll put this on some paper. So we're looking at 2-digit numbers, right? 2-digit numbers. Which are anywhere from 10 to 99. Like they said, the highest a 2-digit number can get is 99. So they're asking how many 2-digit numbers must be in a set in order to apply the pigeonhole principle to conclude that there are 2 distinct subsets of those numbers whose elements sum to the same value. Alright, so say we had a set of 2 elements. Let's just start with a set with no elements. Well, that's silly. Alright, so I'm not going to worry about that scenario. How about a set with 1 element? 1 2-digit number, say like, the set with 10 in it or something. Now there are only 2 subsets in here. The subsets are either the empty set, which will have a sum of 0, and the set with 10 in it, which the elements in this set have a sum of 10. So clearly that's not going to happen for a set with 1 element. Right. then for a set with 2 elements, again, not going to happen. If I had a set with two different elements, say 10 and 11, just using some examples, the subsets are the empty set, which has a sum of 0, the set with 10, which would have a sum of 10, the set with 11, which would have a sum of 11, and the set with both of them, which would have a sum of 21. And again, these are different elements. You're not going to have any set with 2 elements in it who have distinct subsets with the same sum. All right, so let's think. Let's go general. Say I have n elements. N elements. So S equals, 10, 97, whatever. Okay, it's just a set with 2-digit numbers. All right. Now the number of subsets, again, would be 2 to the n. You have the empty set all the way up to the set itself. And this will be the size of the domain. Now the sums, the number of possible sums, well, would range from 0, right? The sums range from 0, which would be the sum of the elements in the empty set, to at most, if you picked all of them, it'd be 99 times n. Right, because every single number is less than or equal to 99, so all n of them added up will be, the sum of all these will be less than 99 times n. Right. So the target, right, so this is the elements of the domain, and then the target has at most 99n, plus 1 elements. All right. So in order to guarantee, that a set of 2-digit numbers has 2 distinct subsets with the same sums, we want the number of elements in the domain here to be greater than the number of elements in the target. So I'm looking for a value of n that makes 2 to the n greater than 99n plus 1. So I'm going to pull up a calculator for this, as they said you might want. And I'll go to I'll go y equals here. And I'm going to go 2 to the x power. And we'll look at a table. And then this one, 99x plus 1. And then I'll set up a table setup, and I'll start at 0, go up by 1, just have it work it for me. Go to the table here, and then look. So again, 2 to the 0 is not bigger than 99 times 0 plus 1. This is powers of 2, and then we want y1 to be greater than y2. When does that happen? Well, it's not happening yet. For x equals 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, there we go. 10. So I need 10 elements. I need 10 2-digit numbers in order to guarantee that there are at least 2 distinct subsets that have the same sum. Because the number of elements in my domain would be 1024, and the number of elements in my target would be at most 991. So I would need at least 10 2-digit numbers. And again, there, show you all that here. So hopefully that made sense. Right? This is, again, was very similar to what was talked about in this example I read out earlier. So if you want to read over that again. And then you finally have your challenge activity. So I'll just talk through one more here, and then you got 2 more levels. So in a standard deck of 52 cards with 4 suits, right? You got hearts, diamonds, clubs, and spades. There are 13 of each card, right? 13 of each suit. How many cards have to be picked to be sure that at least 3 are from the same suit? Right. So how many cards have to be picked so that, now again, you could have it where you have 3 of each suit. I'm sorry, 2 of each suit. Right, not 3. You want at least 3 from each suit. So that'd be 8 cards. You could pick out 8 cards and have just 2 of each suit. But then that 9th card would guarantee you'd have at least 3 from one suit. All right. And then you got 2 more levels where they're basically asking you the same question. So let you play with those. And then you have your additional exercises. Some of these are assigned on your latest assignment, not all of them. I would still, though, even though they're not all assigned, I would still recommend trying them all, looking at all of them. Get better at it, get more exposure, get more practice. You can also look at the solutions if necessary, just to check yourself. But please try to work on the problems first. Try to work them out on your own first before you look at the solutions to check yourself. Because if you're just copying solutions down, without trying, you're not going to learn anything. Okay. All right, and hopefully this video was a good guide for this section. If you have any questions, of course, send me a message and I'll get back to you as soon as possible. And thank you very much for watching.